All right, guys. Sorry about the shaky camera, especially at the end there with my paper not wanting to cooperate. Um, this is first trial, okay? So hopefully things will get better. And honestly, if you guys have serious complaints or concerns about something that I'm doing, please just send me an email and let me know because this needs to be beneficial to you because otherwise, what's the point, right? So if this isn't working for you, please tell me so that we can come up with something else. All right. I hope you also liked our little short guest appearance by Luna. She doesn't understand why I work at home. So yeah, but we're going to keep going forward. So picking up with buffering capacity, right? We've already talked about this. There are two things that affect a buffer and define what range, what pH range the buffer is going to be good in, and that is, think Henderson-Hasselbalch, right? pKa, the Ka. What is the particular acid that we're talking about here, right? Because everything's going to have different Ka's associated with it, okay? So basically, the Ka is going to make a difference. Also, what's going to make a difference? The relative concentrations of the acid and base, okay? And so when we talk about something having a buffering capacity, what we mean is how much can it neutralize before the buffer is no longer able to help, right? And no buffers really have insanely high capacities. There's pretty much a common capacity that we associate with all buffers, and they depend upon the two things we've been talking about. Ka, so what is the acid? And then what is the concentrations of the acid in the base, right? So the greater the amounts that you have of that conjugate acid-base pair, the more resistant to pH it is, okay? That's an example. There's also something referred to as the pH range. And so the range kind of goes hand in hand with the buffering capacity, and that is how big of a pH range the buffer is effective in. When we think about these, you have to go back to the Henderson-Hasselbalch equation, and buffers most effectively resist changes in pH when essentially this is set to 1, okay? When this is set to 1, that is the definition of an optimal buffer, okay? Because if the concentration of base and acid are the same, then the log of that, the log of 1 is 0, so pH equals pKa. And this is what we define as an optimal buffer, when pH equals pKa, okay? And that's why when you're in the lab, we try to make sure that we choose a buffer that has a pKa close to the desired pH, because you remember those sample problems we were working on, this portion right here was not dramatically making the pH any different. The pH and pKa usually at most are 1 unit separate from one another. And most of the problems we worked, it was less than 1. It was less than 0.5, okay? So they need to essentially be really close to one another. By practice, if the concentration of the base is 10 times greater than the acid, or vice versa, if these differ by a factor of 10, your buffer is going to be horrid. It's going to be horrid, okay? Because we want to keep it in the range of where pH is very, very close to pKa. All right, and I showed you sort of a pictorial example of what it looks like when you add a strong acid or a strong base to a buffer. This is from a different textbook, so I thought you might like to see something else. So here we have our buffer, right, that's made of our weak acid and our conjugate base. And when you add a strong acid to it, you're basically adding protons or hydronium. You remember that we say that this is interchangeable. That's going to react with the conjugate base to increase the concentration of acid and water, which basically does nothing. But once you do this, you have to recalculate your concentrations of acid to base to see what the new pH is going to be, right? Because before we were just saying, okay, well, qualitatively, we know that if we add a strong acid, some base is going to react with it, so we're going to end up with more weak acid, so the pH should go down, right? But down by how much? this is how we're going to do it, right? Or if we're going to add a strong base. The strong base is going to react with the weak acid to generate more conjugate base and water. So you notice base leads to the production of base. Acid leads to the production of acid. But it leads to the type of acid and base that exist in the buffer. Okay, that's why these numbers are going to change and we have to recalculate them and then reuse the Henderson-Hasselbalch equation to determine the new pH. Okay, so this involves a little bit of stoichiometry. It's really not that bad. We'll talk about it and then again back to Henderson-Hasselbalch. Okay, so that's it really for this video, because now what we need to do is we need to actually practice this. So we've talked about it qualitatively. Now it's time to go back to pen and paper and actually work this out where we can see what is the new pH of the buffer going to be after we've added some acid or base. All right, so I'm out again. This is the end of the third video. We are still not done. I will see you in video number 4.